Hello and welcome to this lecture with the GM 6L80, 6L90. We're going to cover the electronics and hydraulic operation. We're going to look at the Techem, that's the TEHCM basically, and cover the internal mode switch, what it does. And we're going to look at all the hydraulics of this and see how they operate, point out some important valves and functions. And then we're going to go through and look at some TransGo valves and see how they've modified this transmission so that they last a little bit longer. Let's get started. Starting right off with the Techem stands for Transmission Electro Hydraulic Control Module. It's a mouthful. And inside the Techem, we have a few things. One big thing is we've got the TEHCM built into it. So Transmission Control Module is in the valve body or on the valve body in the transmission. We've got fluid pressure switches. You can see this is pointing at these little circles here. They got switch 1, 3, 4, and 5. 2 apparently didn't make the cut. Number 2 didn't. But then we've got some solenoids. We got inside this little plastic case, which is not removable or serviceable. They've got all these different solenoids in there. So if you have a problem with one, you gotta replace the whole thing. If you've got a problem with one pressure switch, as far as the factory is concerned, you have to replace the whole thing. Now the aftermarket has created replacement pressure switches because that is an actual issue with these transmissions. So anyway, that is how that works. And also built into this is the transmission fluid temperature sensor. And you can actually see that when you're looking at it. It's exposed, but is not replaceable. So if it failed, you'd once again be replacing the transmission electro-hydraulic control module. These 6L80s have pressure switches, as you probably already know. And the thing to know about these pressure switches, like looking at pressure switch 1 right now, pressure switch 1 is exhausting. You can see an O or 0 means it's exhausting. And it's exhausting the fluid pressure at the pressure switch when the clutch is being applied. So this first pressure switch is the 35R. Switch number 3 is the 26. Switch 4 is the 1, 2, 3, 4. And switch 5 is the 4, 5, 6. And also the low reverse, depending on the position of the select valves, the clutch select valves. The way that works too is that these switches are normally closed, so if there's no pressure present, that current will actually be able to flow through that switch. It actually provides a path to ground. And this is of course internal to the TEHCM, so it's not something that we can really measure or check. We can see it with the scan tool. We can observe it with the scan tool. So if the switch never closes or never opens, we know we have a problem. But we can't independently check this because of the way that Techem is set up. And then when fluid pressure is present on the switch, there's a diaphragm type spring in there, and these little fingers go down there and push on those diaphragm springs, and it flattens this out, which kind of lifts the contact off, the lower contact. So it's kind of the opposite of what you might think. With no pressure, there's continuity, and then with pressure, it opens the circuit up. And that's where you could see the problem if these pressure switches leak, if this diaphragm or this film that they have going from one side to the other, if that cracks, then there's going to be no pressure differential on this little piston assembly. If the same pressure exists below the piston as it does above the piston, it's going to want to stay in its natural state, which means like as if there's no pressure, because the pressures kind of cancel each other out, and then you're going to end up having continuity, and it's because I won't have that pressure differential between the top of the film and the bottom of the film. So long story short, when you're rebuilding these transmissions, you do want to pay attention to these pressure switches, make sure these films are intact or in good shape, or really better yet, just change them out when you're in there. Taking this a little further to kind of better understand what's going on with these pressure switches, you can kind of take a look at this hydraulic schematic, and using this one right here for an example, we got actuator feed limit coming in, and you can see it's going, the solenoid is sending pressure to the 1, 2, 3, 4 clutch. The 1, 2, 3, 4 clutch is applied. And if you look, the pressure switch assembly, it's not receiving any of that pressure. So there's nothing finding its way to that pressure switch. So while that clutch is applied, there is no pressure at the pressure switch. If we look at some of these other clutches, for example, this is the 35R, where we've got actuator feed limit coming in, and it actually finds its way right to the pressure switch 1. Whereas line pressure is being blocked. It's not allowed to find its way over to the 35R clutch because we don't want the 35R clutch applied. This is a first gear. But once this actually shuttles over, like once it goes in the third, fifth, or reverse, the fluid in pressure switch 1 is going to find its way out through the exhaust, and then the switch is going to close because it's a normally closed switch. So right now it's in the open state because there's pressure in it. So, because since this is a normally closed switch, it'll be then switched from an off state when it's got pressure. Pressure means off equals off. And then no pressure equals on, because it's a normally closed switch, which means it's passing current when it's in a no pressure situation. Think of it this way. When the clutch is not supposed to be applied, there's going to be pressure at that pressure switch, and that's going to open the circuit up. And then when the clutch is applied, the pressure switch pressure exhausts. Usually the action of the valve is going to cause not only the clutch to apply, but the pressure switch to exhaust, and that's going to give information to the TEHCM. Taking a look at some of these valves that they got in this valve body, and some of these I'm going to point out here are I'm going to say areas that could present trouble if things aren't working quite right. One of the most important valves in this transmission is the actuator feed limit. And it regulates the pressure in these solenoid circuits because it feeds pressure to all the solenoids, and it regulates them to a maximum of 130 psi. So the idea is if you're sitting there idling at 90 psi, so if I've got line pressure coming in, and okay, I said 90, I'm going to say 60 psi. Well, this is a spring that is going to be compressed, and so fluid coming in there, entering into this AFL circuit, is going to work on the end of this actuator feed limit, and once it gets up to 130 psi, it's going to move over and block itself off there. Up until then, it's going to be a wide open passageway for line pressure to find its way in. So basically our pressure is going to be between 60 and 130 in this AFL circuit. And if you look where the AFL pressure goes, it leaves the AFL valve and it feeds every one of these solenoids. And as you'll learn in a bit, these solenoids are going to operate the clutches. Not directly, but they're going to operate valves in the valve body that control pressure to clutches. And based off of how much these solenoids let through to the valves that control the clutches, they're going to be controlling the pressure that goes to those clutches. So it's kind of like a daisy chain. If something failed early on the chain, it's going to screw up everything else beyond it. And this one here is also responsible for so many different solenoids that a failure in the actuator feed limit circuit could be really detrimental to the operation of this transmission. Even though this actuator feed limit valve is considered a regulator valve, it's really considered more of a switch because there's nowhere for pressure to go. If it ever went above 130, if you look, like this thing is supposed to block off that feed at 130 psi, but let's say for some reason there was a cross leak in the system and it got to 150 psi. Well, most regulator valves would move the valve over far enough to the point where it would open up an exhaust somewhere for the fluid to leak out. So that way you wouldn't be able to overpressurize it. And it probably wouldn't happen at 131 psi, but it might happen at 135 or 140. Well, in this case, there's really this thing could just continue to shuttle over to the right, and it wouldn't allow the exhaust of that high pressure. So that was brought to my attention by the TransGo guys because that is kind of a potential situation in these transmissions, because if the AFL circuit ever climbs up high, it's going to overpressurize the solenoids. Solenoids are going to overpressurize the valves that they're operating, like the clutch boost valves and the clutch regulator valves. And if that happens, we're going to jack up the pressures in these transmissions, even like the torque converter clutch regulator valve. All these things are going to get jacked up higher than they're supposed to go. And then that's when parts can start breaking. Not good. Looking at pressure control, the line pressure control solenoid, it's going to take that 60 to 130 psi of pressure, and when it leaves the solenoid, it's going to be between 0 and 130 psi. And that's going to, depending on how it's operating, it's going to present that pressure at the bottom of this pressure regulator valve. It's going to kind of add tension to this spring right here. And if you've seen some of these other transmissions we've talked about, this isn't that uncommon of a operation for these pressure regulators. We got line pressure that comes in, and when pressure builds up, it also gets exposed to the end of that valve. And when pressure gets high enough and it moves that valve down up and compresses that spring, eventually that pressure is going to get into this decreased passage here, and that's going to pivot my pump slide over, and it's going to reduce the output of the pump. It's going to equalize the space around that pump. When it equalizes that space around the pump's not going to have the output it used to have, and we're going to generate less pressure. So that's how they regulate pressure in this transmission. And it's a pretty common way of doing it. You might have seen it already. Now, the reason why the AFL is between 60 and 130, because if you remember, AFL coming in is going to pass everything through it until it gets to 130 psi, and it's going to close it off. And the reason why we're 0 to 130 is because depending on how they pulse width modulate the solenoid, if they have the solenoid PWM'd at about 50% duty cycle, that's equivalent to letting 0 psi through. If I have it at like maybe 10% duty cycle or less, that would probably be equivalent to about full pressure. So it's a normally high solenoid means that when it's off, it lets all the fluid pressure through it. And if I'm letting all the fluid pressure through it, I'm putting maximum pressure on that isolator valve and this boost valve. That's going to add a lot of tension to that spring, which is going to cause a lot of line pressure to be able to work against that pressure regulator valve before it can open up the decreased passage and before it can start regulating its output. This is all important. You know, the reason why it's important is because these transmissions, if they can't control the pump properly, you're going to have either too high or too low of pressure. And if it's not operating the pump correctly, you're like, okay, do I have an issue here at the isolator valve or the boost valve? Or is my pressure regulator valve worn out? Or is my solenoid not controlling it properly? Or is my actuator feed limit delivering it the wrong pressure, which is then feeding the wrong pressure to my boost valve, which is then controlling my regulator all wrong? So everything needs to work properly in conjunction with each other for it to work right. And it's not always going to be something as simple as it needs a pump, or it needs a solenoid, or it needs a valve. It could be anything along those lines. So that's where knowing the whole circuit is so important. As far as clutch control is concerned, if you did the 6T70, 6F50, it is a very similar system. Matter of fact, it's pretty much the same concept, where they take AFL fluid, these individual solenoids for the clutches are going to take the 60 to 130 psi and modulate that into 0 to 130 psi. That pressure works up against this boost valve and the regulator valve. So initially what's going to happen is we're going to move this regulator valve over. We're going to let line pressure into this circuit, and it's going to go over there and it's going to feed my clutch. But what it also does is it finds its way through this boost valve and works its way on the end of the regulator valve and helps that spring out at the end of that regulator valve. And it's not going to take much pressure to be able to move that valve against the blue solenoid pressure. And once it moves it over, let me erase what I got here. Once it moves it over far enough over to the left, it's going to block off the line pressure feed to that clutch circuit. And then as they raise the solenoid pressure up, it continues to let more in. And eventually what it'll do is it'll move this boost valve over to the point where it blocks off the feedback pressure. There'll be none of this in there. We'll have none of that. And then the solenoid pressure is enough to kind of push that valve all the way over to the right. And then we've got full pressure. All this happens within a matter of a half of a second. So they do this so they don't need to have accumulators in this valve body, is they can precisely with the solenoid control how the regulator valve is acting to control the amount of line pressure finding its way into that clutch circuit. They can do a nice smooth increase or a quick increase, whatever they feel they need. And that is, like I said, that's very similar to how the 6T70, 6F50 did it. And so that's not too crazy. Now the 2.6 solenoid and 2.6 clutch circuit in here operates like a more typical pressure regulator system. So we've got a solenoid, and when it turns on, takes that 60 to 130, modulates that to 0 to 130, and that pressure works on this end of that valve, shuttles everything over. I know these aren't colored in, but it's going to end up taking our 2.6 pressure when it energizes, and it's going to deliver it to the 2.6 clutch. That same pressure that finds its way in there is going to help the spring try to close it off. So it's a balance between the solenoid pressure on this side and clutch pressure and the spring pressure on this side. If they need more clutch pressure, they're going to, in this case, it's normally low, so that means when it's off, there's no hydraulic flow. So when they needed more pressure, they duty cycle it on more. They go from 20% duty cycle to a 30%, then a 40, and then a 50. And as they do that, they're going to start increasing the pressure in the 2.6 clutch circuit. Pretty cool, huh? I think so. And now we're going to go through these hydraulic schematics, and we're going to go line by line, color by color, one at a time, for every gear, including every manual range, reverse, and even some theoretical gears that maybe we can come up with along the way. Just kidding, we're not going to go through all that. So this is that housing that spins at a 1.5 to 1. That's supposed to be 2 dots, to 1 underdrive. And you might be looking and saying, what is the deal with this green fluid? Well, our holding clutches are the 1, 2, 3, 4, 3, 5R, and the 4, 5, 6. They have this fluid called compensator fluid, you can call it balance fluid or something like that. So for every one of these pistons, they've got the side of the piston where there's going to be apply pressure. And then on the other side, they're going to end up putting this fluid pressure. And it might only be like 10 psi or something like that. And that basically is there to keep this fluid, this piston off, released when that clutch isn't applied. So they don't want centrifugal force applying that piston by accident. And that's the idea that they've got going on there. And it's all controlled by this compensator regulator valve. So we got line pressure coming in, and then that compensator, that green fluid pressure comes out, and that works on the end of that valve and compresses against the spring. So it's just basically, it's a regulator that controls the amount of pressure that we have, that green pressure, that's that balance pressure. And that's all it does. It doesn't vary its pressure or do anything like that. You can see it literally just has a spring that it has to overcome, and that's it. So it's pretty simple as far as the regulation circuit. Now, interesting enough, this thing has an issue with it. These valves stick, and sometimes they jack up the pressure in this compensator feed circuit. So if you might end up getting way more pressure, green pressure, than they expect or want. They might only want 10 psi, and you know 30 or 40 or 50 because that valve sticks. So if that thing, when you rebuild it, they need to be able to move in and out freely. All this torque converter stuff here. This is the control valve right there, and that control valve is going to receive pressure from our torque converter clutch solenoid, and the torque converter clutch solenoid goes 2 places. It goes to that control valve, then it also comes all the way down here, drawn on the other side. I don't know why they did that. We have our torque converter clutch regulator valve over there. So that one solenoid controls both. And what it's going to do is it's going to reverse the fluid flow. If I am in torque converter lockup mode, fluid is going to enter in on the turbine side of that converter piston, and then anything that's on the cover side of the turbine piston is going to find its way back, drain to the sump. And when I'm in the release mode, fluid's going to come in and feed between the cover and the piston. And to enter that fluid in to the converter assembly, it's going to have to push that piston back. So they kind of do that on purpose. It's a 2-path torque converter. Fluid coming in from the between the cover and the turbine releases it. And then if you reverse that and you drain out the fluid that's between the cover and the piston, and you bring fluid in on the turbine side of the piston, it makes the piston move, And when that friction material comes into contact with the cover, it creates a seal, and then pressure can build up, and then you got converter apply. And that all happens over there on the left side of the screen. They got this converter feed limit valve, which is going to it's like a regulator for the torque converter when it's in a release mode. Okay, looking at more of the schematic here. This is like a full page schematic. It's dumbed down in a sense where they don't have all the different little circuits. They got all the circuits, but they're not drawn exactly how they go. This is like a schematic that you would find in a service manual. I got all my solenoids and my Techem right there. You can see my pressure switches are right here. There's one down there. So that's all good. And then in the middle, we've got our regulator valves, our clutch regulator valves. They've got these clutch select switches, and they're going to do things like allow the one solenoid to operate the low reverse clutch and the 4-5-6 clutch, because they are not going to be operated at the same time ever. So they might as well let one solenoid do both. So anyway, let's take a look at what's happening here in first gear. In first gear, we got the 1, 2, 3, 4 clutch applied, and that is compressing this 1, 2, 3, 4 clutch pack right there. You can see the fluids in this piston assembly. They don't exhaust out the green fluid, it's always there. So it kind of dampens the application of that 1, 2, 3, 4 piston because it's got to squeeze that fluid out. All that fluid was regulated by the 1, 2, 3, 4 boost valve and the 1, 2, 3, 4 pressure regulator valve. And I don't really need to get into detail on how it did it because I showed that to you on the previous slide. If you remember, the solenoid pressure was pushing on that regulator circuit. It allowed line pressure to find its way into the clutch circuit, and that pressure that let in also went over to this boost valve, and that boost valve allowed it to work on the end of that regulator valve, join spring force to help close it off. The more I turn that solenoid on, the more line pressure I'd let in, and eventually this feedback circuit gets kind of cut off, so I don't end up regulating it. I don't end up assisting this spring here on the end of that regulator valve with boost, with this pressure coming from the boost valve anymore. That's the idea. Like I said, everything happens within a half of a second to control the amount of pressure that gets in there, and that is typically what's happening. Now, when I shifted from first to second, if you take a look at the top, all I did was apply the 2/6 clutch assembly. My 2/6 clutch assembly has a simple regulator valve, and it's basically the solenoid is going through and it's working on that valve, and as it pressurizes that end of the valve, I end up allowing fluid pressure to go into my 2/6 clutch assembly, and as they duty cycle that solenoid higher and higher, I get more clutch pressure and my clutch applies. And we shifted into third, you can see my 3.5R clutch applied, 2.6 released. If you remember on that overhaul video, that weld that existed on that 3.5R drum where it broke, it was like right around this area. I'm drawing it like it's a curve, but it leaked right out there. So shot that fluid out and leaked like a sieve. There's actually a little video of that coming up later on this presentation, but that is because of the cracked weld, and you could see how that will burn the 3.5R. I know a lot of people look at this and think that's going to screw up the 1, 2, 3, 4, but it's actually the 3.5R because this piston cavity is right here. The piston actually pulls up and it has these little ply fingers, and it pushes on the pressure plate for the 3.5R. So it kind of reaches in there and goes down into that piston. It's a 3.5R piston and 3.5R fluid leak that occurs on that end that causes the problem. Now the 1, 2, 3, 4 piston, it also has its issues and it cracks. So this piston assembly that's right there for the 1, 2, 3, 4 ends up cracking and leaking its fluid out, and then you burn up the 1, 2, 3, 4 clutch. So lots of things breaking over there. So now we just shifted into fourth. We get to see what's happening with the 4-5-6 clutch assembly. The 4-5-6 clutch assembly, it does have its boost valve, and it has a regulator and a boost valve. So it has that feedback circuit and all that good stuff. So when they're operating it, they're doing that for a smooth apply. And that fluid is going to find its way up against this piston, applies this clutch pack. That clutch pack has the ability of driving that Ravenel carrier assembly. And now we shift into fifth. You can see our 3.5R clutch is applied. We've got our 4.5.6 clutch is still applied. Really nothing different going on other than our solenoids changing their responsibilities. Now we shift into sixth gear. This is our maximum overdrive. We've got the 4.5.6 clutch assembly and the 2.6 clutch assembly applied. And really, like I said, nothing new to show. You're just cycling between these solenoids. The solenoids are operating their responsible valves. Valves are controlling the pressure to the clutches, and there we have it. Reverse is a little different because my manual valve shuttled, and that's going to allow line pressure to find its way into that reverse clutch circuit, or not clutch circuit, but the reverse circuit. And that feeds over and pushes on my clutch select valve. And how does that affect things? Well, my solenoid for the low reverse / 4.5.6, line pressure would come in through it and find its way over to the clutch select valve 3. And you can see we're basically daisy chaining that thing around, and it's finding its way over into the reverse passage for my low reverse clutch assembly. And that is what they're going to do for low and reverse. And also, let's not forget our 3.5R has also got to be applied. So the clutch is going to be applying the 3.5R. So we've got 3.5R, and that's going to drive that front sun gear. And we've got our low reverse, which is going to hold the carrier. And I get reverse rotation. Ta-da! Common failures that they've got in this transmission. The big one is this 3.5R drum that leaks. You can see this air test right here. This weld, it's like a laser weld. But obviously it cracks from either a poor weld or just flexing. This is a little tester that you could put in there so you can air check it. Otherwise you'll hear leaks. This allows you to test it off of the transmission and check it for cracks. Some of the other ones will have other holes, so if you had the 1, 2, 3, 4 piston that's broken, you'd be able to check it and listen for a leak out of it as well. Although you can't see it while while you're doing a clutch test, it should be a tight seal, and if it's not, there's a good chance that that piston's broken. And this is a picture of that cracked piston. If you take a look in this general area, you might be able to see it on the, hopefully you can see it on the video. That is where the crack is. Not good. You lose your 1, 2, 3, 4 pressure. Another common issue are the pressure switches, and the kits now come that you buy now come with replacement pressure switches. So they come with the little films and the grommets, and you have to basically pull your pressure switches out, especially if they're broken. You definitely want to address it. I'd recommend changing them all. And then the trick is, and you've seen it on the video, with the pressure switches, the trick is when you're installing it, because it's kind of difficult. Like you've got the bottom plate, plastic plate of the Techem, and then you got this like top plate, and there's the hole where the pressure switch lives. So I'm just kind of drawing this like that. So the pressure switch would kind of be in this area right there, the actual switch itself, the electronic switch. Well, the rubber grommet, when you go to install it, it fits kind of right in this area here. And the little film that you're sealing against, it lives kind of in between the Techem and the rubber grommet. So that way when you tighten it all down to the valve body, it kind of squeezes this grommet and creates a compression fitting, and it seals off the passage because the fluid from the valve body is going to kind of work on that Techem right there. And it doesn't want it to get underneath the film, or else it won't push on it. It'll be equal pressure on both sides. You need to have it sealed off. And what happens is that film breaks. It just cracks, you know, and then that pressure can get on both sides of that film, and then, like I said, it won't toggle the switch. So it's not going to do what it needs to do, and then you'll set DTCs and all that good stuff. So anyway, that is a common issue. You have to go through and change those. And they, like I said, they come in kits, and some of these tools, that's a homemade tool that I have, but Sonex makes a really good tool to install it. Another common failure is just the Techem, the computer itself, the whole assembly. It could be a solenoid, it could be the computer, and it creates all kinds of different problems. Harsh shifts, flares, binds, it won't adapt, neutral, you name it, it has an issue because every one of those solenoids control different clutches, and if the solenoid's not working right or the computer's not controlling the solenoid right, it's going to have that symptom. So basically what you want to do is you want to look at it and say, did the unit have all the proper clearances when you built it? All the clutch back clearance were really good. Did it air check well? Did you have good solid seals when you air checked it? If so, you probably have a bad Techem and change it. Of course, if you've addressed the pressure switches and all that stuff and it still has an issue, you probably need to change the Techem. Another issue they've got are these plastic check balls. I've never quite understood why they use those. The metal ones seem to beat up the plates quite a bit, but these plastic ones, like that's a normal size plastic check ball. Let me change my colors here. That's a normal size one. You can see this one is substantially smaller, and they tend to wear out. They either shrink in size or they become egg-shaped and they don't seal off, because remember, check ball is going to seal up against that spacer plate, and if it's not perfectly round, it's not going to create a good seal, or it might find its way through the plate if it gets smaller and smaller and smaller. That's kind of what happened over here. It got through the plate and found its way and wedged itself in between a clutch lip seal and the drum. Not good. So most kits will come with the new check balls. You definitely want to put new check balls in there. Valve body and pump issues. These are kind of plagued with pump issues. A lot of times the pump issues come, they get scorn out, they get destroyed. And usually the reason why that is because the torque converter fails, and the torque converter fluid returning from the torque converter gets routed through the oil pump, and then it scores up the pump real bad. Well, also what ends up happening is the pressure regulator valve wears out, and this valve assembly here in the middle is the pressure regulator valve. And this bore right here, it allows fluid to get into the decrease passage. And if it leaks out, it won't let the fluid get into the decrease passage. And if it's leaking out into the pan without finding its way into the decrease passage, you're not going to be regulating your pressure low. You're going to end up with high pressure. This right here wears out as well, but it doesn't seem like this is separating line from converter feed. So you might overpressurize your converter, which that can't be good either. So this is a real common issue. The pump's apparently made out of a pretty tough aluminum. It's hard. It's got a lot of silicone in it. Whereas the valves are not as hard, so they're softer and they tend to tear up the valves quicker. This should be an anodized aluminum, like that brownish color all the way across. So where you see that shiny aluminum is where it's worn out. This is a perfectly good one. There's nothing wrong with this one here. It's the one I had on the overhaul video. This is the replacement setup. They address this wear by putting a steel valve in there. It's not going to wear like the aluminum one. And then in case there's wear in the bore of the pump, you can see they elongated the section there. So the part of the valve body that was riding over this thin section here, that's pretty much got virgin metal in it. Now that the new valve's going to ride on that. And similar situation here where this valve was really worn out. If it took out some of the bore, you can see that with this elongated portion on that valve, they're making use of metal that wasn't wearing on the valve body, or not the valve body, but the pump body. And when you install that, they give you a new spring seat. That's what this does. It kind of slides on there and works as a spring seat for this. And you're supposed to put the bumper spring over, kind of bring that back over. And then this is their new boost valve. So it replaces this boost valve or isolator valve. And they just made theirs out of steel. One thing that the TransGo valve did to address the overpressurization issue is they've added this blow-off valve at the end. So if AFL pressure, that should be a max of 130 psi, if it finds its way in there and tries to work on this isolator valve, or this one up here, that isolator valve is going to try to work on this pressure regulator. If for some reason this goes above, well, its max is 130. I don't know what their blow-off is, but let's just say it's 140. If it goes above that, it doesn't let it go any higher. It just blasts out through this kind of pressure relief valve. So it's a nice little design, kind of a built-in protection there. Another thing they've addressed are these clutch select valves. If you remember, these move back and forth and allow the responsibilities for the low reverse and the 456. It kind of redirects some of the pressure, so you can use the same solenoids in different circumstances. Well, these become sticky. They have pretty light springs on there, and they can hang inside the bores, and they're long valves. So TransGo went through and they created steel valves, a little more mass to them, and depending on the version of the spacer plate that you have, either use their springs or reuse the old springs. But these are set up, if you remember in the overhaul video, hopefully you watch that if you don't put this together until these valves are perfectly free in the valve body, and then once it's perfectly free, then you're good. Another thing that is an issue on these transmissions, but I don't have anything to show a correction for, is that compensator valve sticking. You want to go through and make sure that moves real freely in the bore too. And this is all important, especially if you had metal flowing through it. If you had a torque converter that came apart and all that metal has found its way back into the transmission, you really need to do a good job cleaning the valve body out, because those are the things that hang up the valves in the valve body. Another common failure is a worn out AFL valve or bore. And this is the original AFL right here. And there's nothing wrong with this one. This one vacuum checked really strong. They got a pretty high tension spring on these things. This is the one that regulates pressure to 130 psi max for the solenoids. Well, TransGo went through and they created their own improvement valve. So to address any wear that has occurred in the bore of the valve body, where it gets worn out, they basically install the steel bushing in place of the worn out bore, and they've re-engineered a valve that fits in their bushing, and it's steel on steel, and the spring is calibrated to a little finer control. Really common are torque converter failures on this, and they have two different types of torque converters in here. One of them uses just a standard clutch plate that's usually found in the 6L80s. And these have a tendency of cracking this diaphragm right here. Even though they drilled a nice little circle to kind of prevent stress fractures, still under-engineered, and apparently they can rip those they can rip their those clutch hubs out. So there's a issue with that. And another model they've got has kind of a captive clutch, and they have these straps on the inside that rivet between the cover and the torque converter clutch piston plate. I don't know what you call it really. And these rivets can break off, and that can cause a mess. There are upgraded billet converters, new dampeners, improved parts out there. So depending on your application, if you're trying to do more of a performance build or something like that, or if you pull campers or car haulers and that kind of stuff, you definitely would want to upgrade the torque converter to prevent, this is like a weak link, to kind of prevent the failures from occurring again. Everything, that was it. Everything you needed to know about hydraulics, but were afraid to ask. Hopefully I answered them all for you. Until next time.